Welcome. One of the most important principles in meta-mathematics is the Lauechli paradox. I talked about this recently. It's the paradoxical statement that mathematical results often become easier if one makes them harder. And here are more examples, for example, to show that there is a continuum of Liouville numbers. That's hard to do because you would have to construct a continuum. But much easier is to show that it's generic, which is more general. Harder, seemingly, but easier to prove. Another example was just mentioned by Michael Friedman last Wednesday in the talk about the Poincare conjecture. So Perlman famously proved the Poincare conjecture by doing a harder thing, by proving the Thurston geometrization result of the conjecture. And maybe also philosophical, Grothendieck already kind of formulated this. If you have a problem, you can either go and just use hammer and chisel and hammer it through and just see whether you can do it. Another possibility is to soak the chestnut in water until it's soft, and then the water, of course, is the theory, more general theory, making it harder seemingly, but softening the problem by doing so. And I want to illustrate this with some result which I obtained last week. I was very excited last week about these experimental discoveries that you have for the connection matrix or the Dirac matrix. You have not only the result for the already known result, but we can do it, make it dynamical. So these matrices are defined by a simplicial complex, a finite abstract simplicial complex, which is a finite set of non-empty sets closed to the operation of taking non-empty subsets. And this has a nice calculus. It has an exterior derivative d, and you have then the d plus d star is the Dirac matrix, which produces you this McKean-Singer symmetry, which allows you to prove the Lefschetz fixed point theorem almost for free. And you have also the HT, which is the Hodge Laplacian, and so this decomposes into blocks, and so the kernels of these blocks are the Betti number. So you have cohomology very, very conveniently within linear algebra. Now we can make this dynamical by looking at the dynamical system, by looking at the simplicial map, which is a homeomorphism, right? We have a nice topology on G, which is, G is a set of sets, the topology is a set of sets. So it's the Alexandrov topology, so the points in this space are the simplices, right? These are the elements in G, there are n elements, and so there's sets of sets in G are then open sets, and you can look at homeomorphisms, or you can look at continuous maps, homeomorphism, invertible continuous maps, where the inverse is also continuous, and then more specially at simplicial maps, which is one usually looks at in combinatorial topology. Simplicial maps are given by maps coming from permutations on the vertices. So simplices have to be mapped into simplices, but it has to come from a permutation of the vertices. So I wanted to soften that, and I came and just slithered into this dynamical stuff, because this is kind of very much also related to Lefschetz, because when you have a transformation, what you want to see is what happens in the diagonal, right? The intersection. You want to understand the intersection of kind of the graph of T, right? You want to understand this, and these matrices both kind of shed light on that. So this is kind of for the closed sets, the cores, all the sets contained in X. That's simplicial complex. These are closed sets, and then we have the open sets UX. These are the atoms, the smallest open sets in this Alexandrov topology, and you look at that. So this was the green star formula for T equal to the identity. This is more general. We kind of take here the TX. So it's also kind of like a intersection number. And also for the Dirac matrix, which is also an n times n, the exterior derivative is also an n times n matrix, like a block diagonal matrix, right? So this is the gradient, this is the curl, this is the, these are all the exterior derivatives, all written in one matrix, so that we don't have that mess with, a chain complex and so on. We can just talk about one matrix, which is very nice. And DT is that Dirac matrix, which is kind of a shame that Poincaré did not define this. So Poincaré defined these blocks here, but he didn't look at the whole matrix. The whole matrix would be much easier, because you have then this McKean-Singer symmetry, this supersymmetry, which gives you a symmetry between odd and even dimensional forms, and then you have the cohomology groups, which are the harmonic forms, which you can immediately get. All these can be implemented in a few lines of computer algebra. Also, the dynamical version I've put up, and it just takes a little bit longer, to actually identify when a transformation is an automorphism, so you have to check whether the permutation really preserves simplices. And but this is very, very conveniently, easily implement, and then you can check things, you can experiment with it. So these matrices are not isospectral, so they are in general complex eigenvalues, so these are not symmetric matrices. Also GT, so that's kind of the, but I saw just experimentally, I just saw that they're unimodular still, kind of they're still determinant 1 or -1, which is a little bit surprising, right? Because these are non-symmetric matrices, why should the determinant even be, real? And then we have that the determinant is real is clear from that, because these are real matrices. But why should it be 1 or -1? And then I saw that the LT and the GT are still, inverses of each other, explicit inverse of each other. And I thought also I have to go back to the proofs of the unimodularity theorem, or of these green star identity results, which I generalized over the years. This can be hugely generalized by taking here the different Euler characteristics. And then the next thing is also the potential energy theorem, which says if you sum up over all these potential energies, this is the potential energy between x and y. Now, in a dynamical way, if you take the GT xy, which is the kind of the potential energy between x and tx, like tx has been, displaced, ty is the displaced simplex. So why is it the same? But so that's what I saw. And then I also saw experimentally that this dt are all isospectral, meaning that we don't get a new cohomology. That's similarly with the isospectral deformation of the Dirac operator, or the exterior derivative, which I did, which is kind of in a similar spirit than the Witten deformation, but which also not isospectral a priori, but it's isospectral not for the exterior derivatives, but for the whole Dirac matrix becomes isospectrally deformed, and has diagonal parts. It's still kind of a beautiful symmetry within this geometry. And that's kind of a discrete version. We don't take, continuous deformation, we take discrete dynamical systems. And so this is kind of this is the framework, these are the experimental facts, and then I tried to prove that, and then I got reminded again about this Lauechli principle. Make it harder, make it more general. What is really coming in here? What actually happens, it's very simple once you see it. It's almost disappointing once you see it, that when you look at these matrices, these are actually just the original matrices multiplied with a permutation matrix, which is kind of a unitary orthogonal matrix, or unitary matrix, orthogonal matrix, which has determinant 1 or -1. So we understand immediately why this is still unimodular, and we also understand what happens with the determinant, right? It's actually what happens is this transformation induces a permutation on the simplices, on all the simplices, not only on the vertices, but on all the simplices, and this has a signature, and this signature of this permutation is, the change of the determinant. And more general kind of, there are some linear algebra facts which we could, pose in a linear algebra introductory in linear algebra course, like if you have two matrices A and B, which are inverses of each other, or AB star is equal to 1, and then you take an orthogonal or unitary matrix and you kind of have still that identity here. I leave that to the viewer to do, and also this is kind of a nice exercise in linear algebra if you learn about determinants. Also here for the Dirac, in the Dirac part, we have also something about matrices. We can express it as a linear algebra fact. So this exterior derivative is a block lower diagonal matrix. It's nilpotent. When you take that d square is 0, right? So it's a kind of a lower, there's only these lower blocks are here, these exterior derivatives which go from k forms to k plus 1 forms. And then u is this permutation on the vertices produces an orthogonal transformation permutation matrix on the whole, simplicity complex, and this is block because the k-dimensional simplices are mapped into k-dimensional simplices. So this is block, and then you can just look at this. So au square is still 0, and you have also the Hodge Laplacian doesn't change when you make this dynamical. Which is kind of neat, and it can be even more formulated more generally if you look at that. So the t doesn't even have to come from a transformation. It can also be kind of the Kopman operator. So the u can be the Kopman operator of some, or the time t or wave map if you look at the wave equation, and it still works very well because then what happens is the u, and if you take a wave equation, then it's still of this form, right? Because the Laplacian which drives the wave equation is still of, has still this block form. So it's a very, very general thing, and somehow shows that we have these dynamical systems work very well, both with the connection calculus as well as with the Dirac calculus, which is the usual calculus we have in mathematics in the continuum. And that's it for today.